So we talked a lot about how you calculate line positions, even though in most cases you can find these in databases. We talked about line strengths. It's harder to find those in databases, but they exist. Line shapes, a lot less data available, especially for high temperature gases. That's a more narrow subject, I guess. And that was all in the context of laser absorption as our primary diagnostic tool, using tunable monochromatic laser sources and a line of sight measurement. The nice thing about a line of sight measurement is that it's a path integral, which is a desirable quantity in a lot of problems. But interpreting that signal is influenced by whether or not the flow is really uniform or not. And depending on how non-uniform it is and whether it's temperature or species, you have to kind of think about how to make the measurement worthwhile. But there's a lot of problems in combustion or propulsion where you'd like to have spatially resolved measurements. So you can do line of sight along many lines and do some forms of tomography. That doesn't change the theory. But another approach is to do what's called laser-induced fluorescence. And in that case, we're talking now about a first stage in which there's absorption using a laser, which populates the upper states, which subsequently want to emit light and go back home by emission of light or by a collisional event that takes the molecule back home. That's called a quenching collision. So some fraction of these absorbed photons return through spontaneous emission. That means they're slightly delayed by some amount of time. It also means that if there's some collisions amongst, if these are rotational levels, if there's some collisions, the emission may come from a different level than that was, which is, that's called laser-induced fluorescence. To contrast that with the spontaneous emission that you would naturally see in a flame. So the flames are emitting light without your laser. But if you turn this laser on, you put molecules here, and they are induced to fluoresce. Although the fraction of these photons that come back may be only 10 to the minus 3 or 4 of those that are absorbed because of the dominance of the collisional process that takes these molecules back. So we're going to learn about that. And so the good news about fluorescence is that it's a way to get spatially resolved measurements. The bad news about fluorescence is that it's hard to make them quantitative in terms of the concentration of the absorbing species. So that's the challenge. But you can see motivation is that we can get spatially resolved results. So I'm going to lead you through some of the history, typical experimental setup, two situations, whether steady state illumination or pulsed, and the simple model that we usually use to describe this process called the two-level model. And then we'll look at the detection limits that are achievable, and you'll see that you can detect really a small amount of an absorber. And then we'll look at something called characteristic times, which will help us understand how to think about this process when we're applying it. There's a section here on modifications of the two-level model, and it's about 8 pages long in your handout. I think it's PowerPoint pages 28 to 35. There's a lot of detail in there, and I think I won't go through it. I'll leave you to read it, and if you've got questions later, you can email me. But I think it's just too dense for this lecture, so we'll probably just focus on this first 6 sections this morning in the first hour and leave you to read the other material. So laser-induced fluorescence is really laser-induced spontaneous emission. So we always have spontaneous emission. Anytime there's excited states, there's a probability A per second that some emission will take place. Therefore, the amount of emission that takes place is proportional to the number in that emitting state and the A coefficient. The population is usually produced by collisional events. So what we're doing is we're going to send in photons and accelerate that process, put in an overpopulation in that excited state beyond the Boltzmann distribution, and watch what happens. So that's a multi-step process, absorption followed by emission. So we have a pulse or CW excitation, followed by the potential for a collisional change. In fact, it's highly likely that there'll be collisional change because these collisional events that change rotational levels, assuming we have a molecule, those collisional events have a high frequency. So remember, the collision frequency in this room right now is about 10 to the 10th per second. So a molecule is having, on an average, is having 10 to the 9th or 10 to the 10th collisions per second. Whereas the A coefficient, even for an electronic transition, may only be, say, 10 to the 5th per second. So in other words, there's a lot of time before it emits for it to have collisions, if you're at atmospheric pressure or so. So that's the way to think about this. It's a slightly delayed, so slightly delayed by something like the radiative lifetime process. It's not instantaneous, but it's still fast compared to most flow times. This is a complexity here. We have to deal with the fact that we may be changing the wavelength of emitted light because of that collision process. That also means that you can get multiple states populated by this process before it emits. So you may be getting emission from multiple upper states. So it may be, it'll be a change in wavelength from that which you send in. And it may come from multiple states. And it's not instantaneous, even though it's very fast. So why do we care? We care because it's the way to get spatial resolution. Typically, not always, the observation is made perpendicular to the illuminating beam. So the light beam comes in. It's usually focused. It's not focused to a point. Light can really only be focused to a waist. But it's focused so that the diameter of this beam here might be rather small. And then you collect the light at right angles, typically, by some sort of a lens with a solid angle omega, or lens diameter d, separated by a length L, focused onto some kind of a detector, which might be a photomultiplier, something that kind of is a quantum detector, meaning that it is sensitive to individual photons. It's not a thermal meter, it's not a bolometer, it's a quantum sensitive device. Typically, if you're going to make a measurement from one location, this would probably be a photomultiplier. So that means that in the absence of any other problem, all the light you collect comes from this small volume right here. So if you imagine the laser is responsible to produce the excited states here, and you collect that some amount of that emission on this detector, you've made a spatially resolved measurement in that volume here. It's essentially the area times the length. When we go to the planar variation of this would be some sort of a sheet of light with some thickness. And these might be individual pixels on a camera. So that's the idea. It's possible then to make this rather small. Now, what's the issue? Of course, the smaller you make this, the smaller the number of, for given laser power, the smaller the number of molecules that are emitting. Therefore, your signal will go to 0 in the limit that this goes to 0. This spontaneous emission actually goes into 4 pi steradians, goes into all angles. And since we only collect omega solid angle, the fraction of the emitted light we collect is omega over 4 pi. So immediately you see we might lose 99% of the emitted light if we do this in this way. So we're now talking about collecting a small fraction of the light, and we're anticipating that of the absorbed photons, we only a fraction of those are re-emitted. So how do you deal with that problem? Well, you just send in more photons. Send in more and more photons so that you get enough out. And we'll see that it doesn't take that much power to make this work. I like to think about this as spectrally resolved. So you imagine that we are varying the wavelength of our narrow line with laser across an absorption line. The fluorescence should mirror this, roughly. If there were not a lot of upper state energy transfers, the shape of this fluorescence line would be basically the same as the absorption. So I like to talk about spectrally resolved fluorescence. Not many people do this, but I think it's a good strategy. Okay, so this can be species specific, because if we picked an excitation wavelength peculiar only to the species that we're trying to probe, that is in the absence of interference absorption, then the emission is going to also come from that species, usually. So it can be species specific, and it tends to be much stronger than Raman scattering. So absorption is strong, fluorescence is diminished by what we'll learn to be the fluorescence quantum yield, and and it's still stronger than Raman scattering. So every method has a use, but in terms of signal strength, fluorescence is stronger than Raman. If you think about it this way, of scanning the laser across this line, then you realize that the fluorescent signal itself is riding on a dark background. That is, you don't get any fluorescent signal until you reach the line position. So that's an attractive feature. Always nice to have a signal for which there's some reference background level to help you distinguish noise. Now you can use LIF to measure a lot of different things. In the early days being probably 1980 or so, the chemists were the ones who were really interested in laser-induced fluorescence. And the lasers were emerging, and they realized they could detect very small levels of species in a mixture. Not necessarily a flame, just a mixture of gases. So it's because it's dependent on the absorption spectrum, specific to a molecule. So the things we might be interested in measuring would be the number density in the quantum state, density of species I in a state described by all of our quantum numbers. Of course, as combustion people, we're always interested in temperature, or maybe we want the species concentration, which we could get once we know the number density, and if we know the static pressure, and we know the temperature in the Boltzmann distribution. Pressure can be important if it's a flow in which the pressure is variable, like a compressible flow, supersonic flow. Pressure is not uniform. Sometimes we need to know the pressure. We might get that from the broadening of the line. And of course, we can get the velocity from the Doppler shift. So there are ways to use laser-induced fluorescence to measure all of these quantities. And over time, people have measured endless number of species. In the early days, a lot of the chemists were interested in measuring trace levels of atoms. Maybe, let's just imagine, say, arsenic, something like that was present in low concentrations, and the analytical chemists wanted to find a way to measure these low concentrations. Maybe from a combustion point of view, we're typically interested in radical species that are responsible for the pace of combustion chemistry. Stable diatomic species, polyatomics, all of these things have been done. And by the way, some of the chemists would be doing this with liquids. We're talking here about gases, but same ideas apply in liquids. Many atoms, 100 atoms probably, an endless number of atoms. So if we think about absorption, it's the transition between a lower level and an upper level. If we tune our laser to a wavelength where only those two levels participate. And we think of it as being instantaneous. The time it takes for the laser light to pass through our sample volume is negligible, and the time it takes for the electron to change orbit is negligible. I told you it was 10 to the minus 16 seconds. But it is a line-of-sight method which has advantages and disadvantages. In this case, what we care about is the ratio of the incident and the ratio of the transmitted to the incident light, or the difference, amount of light absorbed. Fluorescence is a delayed process, not instantaneous, but typically fast. Now, why is it fast? Because it has a propensity to radiate at probability A. 1 over A is really the longest that it's going to be there. But it can be a multi-step process if there's some collisions going on up here. You can do this with either a CW or a pulse laser, and you can do it with a narrow line width or a broad laser. So there's all sorts of combinations that are used. I wanted to give you a little bit of history. The developer of the flash lamp pump dye laser, remember the dye lasers were really the first ones that allowed you to tune wavelength, tune the wavelength of light. So that was the first medium that allowed a laser in which you could adjust the emitted wavelength. And the person who usually gets credit for this is Schaefer from Germany around 1966. Remember, the laser was invented about 1960, 61, about there. So different, and those lasers were initially fixed wavelength lasers of different types, usually some were solid state, some were gases, but they were electrically driven. So notice this says flash lamp pump. So you always have to excite the laser medium. It might be a flash lamp. In those days, you would use a flash lamp. So a discharge of, say, electrical discharge in which the lamp was filled with some gas or emitted. So you use electrical energy to produce a flash lamp. That energy would be focused into the dye laser, which was the gain medium. And that dye laser would be in an optical cavity, which forced the light back and forth along a given path between reflective mirrors so that you can have gain. So you produce an inverted medium that has gain, and then you allow some of that emitted light to go back and forth and promote induced emission. That's the basic idea of a laser. Along about 1970, we evolved to a continuous wave dye laser. So now the pump source was typically an argon ion laser. So there'd be electric discharge plasma argon ion laser, which was continuous, and it might be a kilowatt of power, and that would be used to excite the laser continuously, the dye continuously. 1980, people figured out that if you had this light circulating in the cavity, in the visible, you could pass that light through a crystal, and if it was intense enough, you could do frequency conversion and produce light at half the wavelength, which is twice the photon energy. That's a nonlinear process, which means that you have to usually pump, you have to have enough intensity to make this happen. That was done in what's called a ring dye laser cavity, so that the light kind of went along the figure 8 and only went in one direction. So all these optical engineers were clever. They could make the light go in only one direction, unidirectional, and they would have the gain medium, and they'd have the frequency conversion crystal, and so in this circulating cavity there would be both visible and ultraviolet light. So that's how we got to UV light using a frequency doubled ring dye laser about 1980. I had one of the very first ones. Spectrophysics was the company that made them. Eventually, the most common pump laser source was a neodymium YAG laser, it's called, neodymium doped yttrium aluminum garnet. So a solid state material, which when subjected to a flash lamp, would emit light usually at 1.06 microns. That was a very real, in fact, till to this day, neodymium YAG lasers are very, very popular. A little bit later, excimer lasers were developed, and they're another fixed wavelength, high intensity, efficient laser, typically in the ultraviolet region, a few different wavelengths, depending on the excimer. Those things surfaced around 1980. And then finally, a little bit later, I can't remember when, maybe 1990, I had a student who learned how to make a rapid scanning ring dye laser, so it could be rapidly tuned. These commercial products here were tuned very slowly, but my student figured out how to do this rapidly. So we did CW, wavelength scanned LIF back in that period of time. Why? So that we could do spectrally resolved absorption with fluorescence detection. That has some benefits. Then about 1981, also in my laboratory, we had the first two-dimensional imaging of fluorescence. And first we called it quantitative imaging, and then that evolved to, some people for a while we called it 2D LIF, and then we started calling it PLIF, planar laser-induced fluorescence. So I guess it was, and we did this was the first PLF image taken, it was around 1981, published in 82, I think. This was kind of a simple burner in the laboratory, and this was a single shot of the OH distribution in its flame using that method. In those days, cameras were very, very, in fact, we made what might have been the first intensified digital camera using a photodiode array. Now you can buy them and they're produces a lot. This was actually a 100 by 100 array detector, which just means only 10,000 pixels. Now they have a million pixels. But in that period in time, that was a lot of data. And that 100 by 100 array in a snapshot took us about 40 minutes to print it out onto a pen plotter, if you guys even know what a pen plotter is. So anyway, this is basically a printed image taken by false color image based on intensity. Essentially, it's a snapshot of OH distribution. Now you can see where it is. So it's temporally resolved spatially resolved, but what's the OH concentration? That's the challenge, as you'll see. A little bit later, one of my students started doing this in a spray flame. So this is a spray flame, scattering from the droplets in the spray. And there's the OH distribution in the background. So this was a few years later, maybe 4 years later. Quality of the image was getting a lot better. Now we had a better camera, better computer. So that took us to about 1985 or so. Then we became interested in measuring imaging temperature and nitric oxide, and we tried to do velocity about 1989. I was motivated in this PLIF by seeing some movies by, there were fluid mechanics professors who would calculate flows in a plane, and then they play movies. I thought, gee, that's what we should do experimentally. We should actually attempt to make movies of the species distribution in a flame, transient flame. But because we were measuring OH, my fluids colleagues were not interested in OH. It's too complicated. So we decided, let's find a way to image room temperature. And so one of my students discovered acetone as a ketone is a family of chemicals. And he discovered acetone as a way to seed room temperature flows that could be studied for fluid mechanics purposes. So the laser became simple, the camera became simple, the theory became simple. I think I'm going to talk about that either in the second or the third hour. That got their interest. Then we got interested in supersonic combustion. Imaging in 1993. There was interest in going to high pressures for a while, imaging up to, I think we imaged up to about 50 atmospheres. Then I had an idea, well, why are we always imaging in the ultraviolet and the visible? Why don't we attempt to do infrared? Well, the reason no one would do infrared is you'll remember that the Einstein A coefficient for infrared transitions for CO is 30, not 10 to the fifth. OH is 10 to the fifth for A. CO infrared emission is 30. In other words, the orders of magnitude smaller. So the propensity to emit light is so low. Why would you do this? But if you think about it, I'm going to show you. If you think about it, there's a reason why it still is very attractive. But very few people have done this. Some people in Sweden have done it. Not commonly used. Along about 2000, now I'm thinking about the evolution of mostly PLA. People started getting fast lasers, pulse burst lasers, so that you can maybe, instead of doing this at, say, 10 hertz, the YAG laser, start doing it at high speed. That was important. We discovered around 2004 that when we were trying to do nitric oxide and oxygen in a flame, we were getting some extraneous emission. We found out that hot CO2 actually fluoresces also. That wasn't really recognized till then because people hadn't studied the high temperature spectrum of CO2. Now the trend is towards really high speed, 5 kilohertz PLIF, or even faster. And once in a while we go back and we try to do CW PLIF. It has some advantages. Okay, that's just kind of a history. It takes us up to approximately now. So we're back to the arrangement that's typically used. You have a laser, CW repulsed, some sort of optical system that forms either a waste or a sheet of light, a volume element that can be of the order of a cubic millimeter, depending on what you're trying to study. How much spatial resolution do you need? Is 1 millimeter enough? 1 centimeter? 10 microns, you have to decide. And this might be a flame, a flow, a plasma, whatever. And now this is a high intensity beam typically, so usually there's some sort of a trap or power meter over here to see what's happening. And again, typically you collect with some solid angle omega, recognizing that omega over 4 pi is the fraction of the emitted light that you're collecting. We want that to be big, but it's hard to make this very big unless the experiment is pretty small. That's another problem. Okay, now this light goes onto the detector. It might be a photomultiplier, PMT. And now you have to decide whether you're going to, what wavelength you're going to collect. You might put a spectral filter here to narrow down and separate out any emission from this region. Or you might try to take this light and put it into a spectrometer in order to disperse it and look at the emission intensity as a function of wavelength, because it's going to be different than the wavelength of excitation due to the subsequent collisions. There's a lot of variations on this theme. So there's a variety of recording modes. You might fix the wavelength of detection maybe with a filter here. You might measure then the emission intensity at a fixed wavelength. Or you might spread out the fluorescence spectrum onto a spectrometer and measure the intensity as a function of wavelength that's emitted. Even though you absorb at one color, the emission cannot come out as a spectrum. That's called the fluorescence spectrum method. So there's the fluorescence spectrum and there's the excitation spectrum. In the excitation spectrum case, you change the wavelength of the source while you hold this fixed. You can decide whether you're going to detect spectrally narrow or spectrally broad, but the variable over time is you vary the wavelength. That's called an excitation spectrum. That's essentially an absorption spectrum because the fluorescence light is coming out in proportion to the absorption. So you're scanning the excitation over the absorption feature or features. And of course, instead of just using a photomultiplier or spectrometer, you could, it looks like my pointer's dying. Die too. So you could also use a detector here, which would be a CCD device or anyway, a two-dimensional detector, a ray detector. Now, you also could be deciding whether you want to do, this is a pulsed experiment that you're just accumulating the signal, or whether you're going to try to resolve. What if we have a pulse laser, and now we look at the fluorescence, which might have a temporal behavior like this. The reason it has a longer decay is that you populated the upper states, and it takes time for them to diminish. So there's temporal information. So there's a lot of possibilities here. Changing the excitation wavelength, changing the detection wavelength, pulse lasers, CW lasers, whether or not you want to measure transients. There's a lot of variations in this, in laser-induced fluorescence. Now, the fluorescence volume element, which would be, say, the length that you're going to look at, set by the size of this detector and usually some aperture, determines that length. And the waste is determined by the optics. So a typical number might be of the order of a cubic millimeter, but it can be smaller. Bigger is more signal. In the end, what's going to happen is the signal is going to depend upon the number of photons passing through this volume, or the laser energy, and the number of absorbing molecules in that volume, and the fraction of the absorbed photons that are re-emitted. It's going to depend on that. Typically, it might be in this range. Solid angle of collection. It's usually done in solid angle. So that's the lens area divided by this length squared. That's the definition of that solid angle. And so if you write this in terms of optical components, some people would recognize that as 1 over the f number squared. Clearly, small f number is going to allow you to collect more light. So you'd like this to be a big solid angle, which means a small f number. Of course, as the f number gets smaller and smaller, it can get more and more expensive to get a high quality lens. So some of these lenses used in fluorescence could be $3,000 to $10,000. If the f number is 2.5, which is achievable, then omega over 4 pi is 0.01. In other words, you only collect 1% of the light that's emitted. That's pretty inefficient. That's a problem. That's weakness. So you overcome that weakness usually by sending in more photons. Now we can start asking, how strong is the signal level? So we can imagine our 2-level system, which holds up even when we have many levels. And so we just imagine that we're talking about emission from 2 back to 1. So we've excited level 2 somehow with a laser, and we produce some excess population in level 2, and the probability of it emitting back to a specific level 1, which would tell us the wavelength, the probability of that happening per second is A21. Under steady conditions, the number of photons that we would see per second by this process would be the total number of molecules in level 2 times the probability of emission per second over 4 pi. So this is, imagine a steady situation. This is the emission signal we're going to see in photons per second onto our detector at this wavelength. Is the number of emitters, total number of emitters in the emission volume, probability per second of emission times the fraction of the emission we collect. Or in terms of the number per unit volume, I usually use in lowercase for number per unit volume. Be number per unit volume times the volume element, A21 over mega over 4 pi. So the power that we collect is the number of photons per second times the energy of the photon. So if you want to do this in power, it's the photons collected per second times h nu. We don't know what that is yet. But we can immediately say that's the strength of the fluorescent signal. If you collect light of this color, that's what you're going to see. Now, if you note the signal then depends really only on some constants. We presumably know V, we presumably know A21, presumably know omega over 4 pi. The signal depends entirely on N2. So this is a measurement of N2. Usually what you're after is N1. So the relationship for what we're measuring is pretty clear. The question is, what's N2, and how does it relate to what we're after, N1? Well, because this is an inefficient process, most of the time this is used as a pulse laser. So let's look at the same relationship in the case where we have a transient signal. So now the number of photons per second, or the number of photons collected, number of photons collected is the integral over time of the population produced in 2 dt. So here's the same constants in the problem, only now instead of having a steady value of N2, we recognize that N2 is a function of time. So we pulse the laser, we populate N2 with some transient amount, but whatever it is, that's the signal. So this N2 of time depends upon the laser and the process that we're going to use, but the result is still easily expressed in terms of N2, but now N2 is a function of time. Well, the way people think about this, or the way they thought about it initially, was back to the same diagram that you've seen before when I introduced the Einstein theory. We have to recognize that we have 2 levels. Now, the molecule may have several levels, but we're only pumping this one. And it will go here if we fix the wavelength. So this is an allowed transition. And that's the so-called induced absorption. So the number per second, number per unit volume per second undergoing this process is the number per unit volume in 1 times W12. So you know that W12 now has the units of per second. That's the probability per second of going from 1 to 2, multiplied by the number that are in 1, and that's then the number going from 1 to 2 per unit volume per second. Clearly, this depends upon the laser intensity and maybe a line shape function. So buried in here are the laser properties and the Einstein coefficients. But it's common to write this as W. If you're illuminating at this wavelength, you also can drive molecules that are here back down, although the population here may be very, very low compared to this one. So this process is usually negligible unless you have used such an intense laser that you've produced such a high population that you have to think about this. Meanwhile, in this problem, some number of collisions per second are occurring that happen to be populating this level. And the rate of that would be the number in 1 times the probability per second of collisions taking you from here to here. Obviously, that depends upon temperature and the collision frequency, the pressure. It's also true that collisions can cause reduction of this quantum state to this state, and that's called a quenching collision. This one is usually negligible because this energy gap is so high that the collisions don't make this happen very often. So the whole idea of laser-reduced fluorescence is you can overcome this process by just pumping hard. This W12 becomes much bigger than this Q12, so usually this term's negligible. This one is important and is a problem. And here's our fluorescence signal. So the number per second per unit volume is the number in 2 times the probability per second of this particular transition. Now going back to the Einstein theory, the probability per second, this W, if we integrate over the line, we call this W12. But if we have a spectrally narrow laser, we actually have to think of W12 in a specific frequency range. And I don't like the Einstein units. They're kind of crazy, so we always substitute in terms of a laser intensity. So we always, and there's sometimes there's written with a rho, and there's different ways of writing this thing. So I just quickly substitute in terms of the laser intensity. It's easier to keep track of. So now, typically, this one is negligible. This one we have to keep track of. This is our signal that we're after. Typically, this one is small because if we pump in the so-called linear regime, weak excitation, then this one is negligible. If we pump hard and try to saturate, I'll tell you about that in a little bit, we got to leave this one in. Now, if you anticipate it's a weak process, you're probably going to use a pulse laser. Pulse lasers are spectrally broad because when the pulse length gets shorter and shorter, the laser gets wider and wider. So the width of the laser might look something like this compared to the absorption line that might look something like this. Therefore, only a fraction of the laser light is actually useful. But the more important point right now is that that means that the intensity, spectral intensity is watts per square centimeter per unit frequency, is kind of constant. And so we can treat it as constant across the line and kind of simplify our analysis. And that's how we get to N1 W12, having done this as a function of frequency first. That means we integrate out the absorption line shape. Keep track of that. Remember, our absorption lines are of the order of 1/10 of a wave number at STP. And these lasers might be 0.5 wave numbers or more. Now, how do we solve? Remember, we have the signal in terms of N2. How do we figure out what N2 is? So in chemical kinetics, the usual thing you do something called a rate analysis. You write the time derivative of the population N2 as the excitation rate minus the loss rate. Then you argue that, well, the time rate of change, this term over here is small compared to these individual terms, and so you set this to 0. That's called the steady state approximation. It doesn't say that N2 is equal to 0. It says that N2 dot is small. So that you can solve then for the number density N2 in the steady state model, and it's a ratio of the excitation rate divided by the sum of the depletion rates times N1. Now we're getting close. This is what we'd like to know. And we can get there if we know these other terms. So we have a solution for N2. That's good. So the entry-level model, we call this the two-level model, says that the N2 steady state is N1, the quantity we'd like to know, the number density in the absorbing state, is the ratio of the excitation rate divided by the sum of these three possibilities. And now we look at two limits. One's called the weak excitation rate, usually called linear. And then there's the strong excitation rate, that's called saturated. Why this appeared right here. I think that's supposed to be a little bit later. In the weak excitation limit, that means that this W21 can be neglected relative to the others. W21 is small. You have to remember that back from the Einstein theory, that G1, that's the degeneracy, B12s and B21s are related this way. That whatever B12 is, B21 is about the same, only by the ratio of the degeneracies. Okay, so what we argue is that this, in the weak excitation limit, that's basically saying W12 is kind of small, therefore W21 is small compared to these two, and then we're going to make that approximation. This limit, that means that N2 is small compared to N1, and therefore N1 is hardly changed, so we'll just write it as unchanged. Or we'll write it as N10 is the sum of N1 plus N2. If you make that approximation in this weak excitation limit, N2 is the thing we're after, the unperturbed N1 times this ratio. And this will apply as long as W12 is small compared to this. Of course, if W12 is small, that means our signal is going to be small. So now we're saying, I want this, my signal is related to this, I can get what I want if I know these numbers. We know A, that's just the Einstein coefficient. W12 and Q21 are the remaining problems. So if we do this in photons per second, we go back, our signal is N2 times the volume A omega over 4 pi. Looks like I have 2 pointers there. Well, they'll work temporarily. Okay, so I can write now, I substitute my relationship for N2, rewrite the terms a little bit, and now I can see, if I look at this, and you can read it here for yourself, this is nothing more than the photons absorbed times the fluorescence yield. That's the fraction of the photons emitted compared to those that are fluorescent collected. So the way I like to think about this, photons out is photons in, fraction absorbed, fraction of those which are re-emitted, and the fraction you collect. So if you want to get more light, those are the three possibilities. Collect bigger fraction, improve the fluorescence yield, get greater absorption. How do I get greater absorption? Send in more light, look at a bigger volume. That's it. So photons out is photons in, fraction absorbed, fraction emitted, fraction collected. So we're getting close to what we want. We know this or can measure it. We know the Einstein coefficient. We know the laser intensity, or we can measure it. We know A. The only thing left is Q. Okay, let's see. Okay. There's different ways of thinking about this. I'm not going to go through it. But I like the photons out is photons in, fraction absorbed. Photons absorbed per second is photons in, some fraction absorbed. Fluorescence yield, fraction collected. Now there's another limit. What if you really crank up the laser power to the point that W21 is actually bigger than A plus Q rather than much smaller? That's called the saturation limit. Now you can show in that steady state approximation that N2 equals N1 times the ratio of these W's. Or in other words, N2 is N1 times G2 over G1. So if the degeneracies are equal, they can be. You actually have you've saturated the transition, and you put half of the population in 2. You can do that. Well, I don't know how much power it's going to take, but you can do that. So if we remember this, so in the case where the degeneracy is equal, which is fairly common, you've actually put half the population in 2. You're sending in photons, so many photons. You're pumping them up that the excitation and the de-excitation rates become equal, even regardless, independent of Q. Now, if you had a simple 2-level model only, the total number is only those in 1 and 2. And in this case, then you have number 2 is just half of what you're after. Good, you're going to get a big signal this way. So the fluorescent signal in this limit turns out to be N1, 0 that you're after, ratios of these G's, volume A, omega over 4 pi. The good news is we got rid of Q because we don't yet know what Q is. So people love this idea. It's just that it's hard to accomplish in the laboratory. Virtue is it no longer depends upon Q or the laser intensity, as long as the intensity is high enough. The problem is it may be difficult to do in all parts of the laser beam. So if you imagine a Gaussian distribution of this laser beam, there are weak sides at which you're not saturating. So as a concept, it's got a lot of potential. The question is, can you achieve it in the laboratory? If the intensity is not sufficiently high, you're somewhere in middle ground. And there's a theory for this too. I won't go through it. You can solve for the steady state answer for all intensities, for all values of W12 and Q21. When you do, you get a more complicated expression. So the signal divided by the saturation possibility, 0 to 1 now, depends upon this quantity, the sum of the B's. Anyway, there's a standard plot. And you can do this now for different values of Q and A. And depending on what they are, you're in the linear regime or you're in the saturated regime. 2-level model, let's look at some typical values to get a feel for this. Typical value for OH is about 10 to the 5th. The typical value for an atom is about 10 to the 8th. It happens to be about 10 to the 6th for NO. I said 10 to the 6 here, but it's really more like 10 to the 5. And 10 to the 8 for atoms. What's Q? Well, Q is a collision frequency. It's the collision frequency for which 2 goes to 1. And if you say, well, practically every collision is going to make that happen because it's exothermic, you can go back to the collision theory we did early and you can solve for this. So as I keep telling you, collision frequency is about 10 to the 9th to 10 to the 10th in the room right now. So it could be that once you're in an excited state, you will have a collision with something in 10 to the minus 9th or 10 to the minus 10th seconds. And if that is an efficient process of quenching, Q could be as big as 10 to the 9th. What does that mean? That means that A over Q is a small number. Here's A, here's Q. So in most cases, at atmospheric pressure or higher, A over Q is a small number, which is telling us already that once the absorption takes place, the probability of emission, A, is smaller than the probability of quenching, Q. If this number is 10 to the minus 4, that means that I have to absorb 10 to the 4th photons to get 1 emitted photon. But since I only collect maybe 1%, now I got to absorb 10 to the 6th photons to get 1 on my detector. How do you solve that problem? Well, you send in a lot more than 10 to the 6th. So the fluorescence yield, it has the physical meaning of the fraction of the absorbed photons which are re-emitted as a photon. And it tends to be a small number, except when you go down to really low pressure, because then the collision frequency goes down. So if I reduce the pressure by 3 orders of magnitude, I go from 10 to the 9th down to 10 to the 6th. Now they're starting to be competitive processes. So you might say this is worrisome, but you'll see it's not. But this is where I began to think, I don't know, this may be 20 years ago, I began to think, well, why is it we don't use the IR? The problem is, well, A is so small, you think you're going to be dead in the water. But it turns out that when you think about it, the Q for an electronic transition is this big number up here. But Q for infrared has to do with transfers between other energy levels in the ground electronic state. That rate Q for these processes actually can be quite a bit smaller. It turns out that A over Q maybe isn't that bad for the infrared. That's the whole idea. Okay, here's some typical values for electronic transitions. Virtually everybody does LIF for electronic transitions. So what are the terms here that we have to worry about? And the question is, how big does I nu have to be for saturation? So you look at this expression here, and you want this basically W1, W21. W12 or W21 are the same. So we can imagine now 2 cases, or low Q or high Q. If you do low Q, then the question is, when is the saturation intensity is that which is required to make A over B a big number. So on for high Q. So you can go through this and you can solve for, and I'm not going to go through it in great detail. You can put in some representative numbers for wavelength, and you can solve for the relationship of B21 and A21 in these limits. You have to make some assumption about Q. You assume it's about 10 to the 4th, meaning what if Q is 10 to the 10th and A is 10 to the 6th? And when you go through this, you can solve for the that intensity required for saturation. And it'll come out to be, in this case, 0.4 watts per square meter per hertz. But that won't mean much to you yet, but it's achievable. Continue. So I'm going to continue on this. I want to do this now in terms of power to make it easier for you. I'm not going to spend a lot of time on this. You can read it. Intensity, the intensity is the power. Remember, spectral intensity is the power per unit area per unit frequency. So if we take the power of the laser divided by the area of illumination divided by the bandwidth of the laser, and if I let the diameter be 1 millimeter and the laser width to be 0.5 wave numbers, I get a number here of the 0.5 wave numbers or 10 to the 5th hertz. Now I can solve for this in terms of power in watts, and you'll go through it and you'll find that the saturation power for the case I've considered, where the ratio of Q over A is 10 to the 4th, and the wavelength is 500 nanometers, and I get a power of 5 kilowatts. So now you're starting to get a feel for this. I would need about 5 kilowatts of power illuminating my 1 millimeter diameter region to saturate, meaning I'm going to put half the molecules in the excited state. There's other questions about, well, are molecules really two-level systems and so on? And that's a problem, but we can overcome it. So you might look at this and say, wow, that sounds like a big number, since I remember Professor Hanson saying our diode lasers are 2 milliwatts. So we're not going to saturate with a diode laser. 5 kilowatts is not as bad as you think. That's too much for a continuous wave laser. But what if we go to our neodymium YAG pump dye lasers, which typically can output 1 to 10 millijoules or more in a 10 nanosecond pulse at 225 nanometers. That's 10 to the 5th watts. Why? Because it's 10 to the minus 8 seconds. So instead of having 10 millijoules per second, which is what I have with my 10 milliwatt diode laser, I'm going to do it in 10 to the minus 8 seconds. So I just picked up a huge benefit. So it started to look, maybe this isn't so bad. Therefore, it's easy to saturate within the limits of a two-level model. And atoms come closer to a two-level model. It's harder to do with molecules because it's farther removed from being a real two-level model. Atoms can be kind of like a two-level model. And you can see that the problem gets worse as pressure goes up because collision frequency is harder. So the competition of Q gets bigger and bigger. So it is achievable, according to this simple analysis. And it has been done. Now I send one slide here on the vibrational case because I like this. But now our A values are quite a bit smaller. Remember, it's about 30 for CO. But what is Q? Q is some sort of a de-excitation rate. It might be what's called a vibration translation de-excitation. It might be a VV transfer to another species. It's usually dominated by this. But it turns out these numbers are a lot smaller than the 10 to the 8th, 9th, or 10th. So in fact, the fluorescence yield is actually about the same as it is for electronic transitions. Now, that doesn't mean we're home free because the absorption is weak. So remember, photons out is photons in, fraction absorbed, fraction emitted, fraction collected. So for the same collection efficiency, our fluorescence yield can be about the same. Yeah, but the fraction absorbed is low. So this is only going to work when you do a infrared species that's of high concentration, like CO, CO2, combustion product. We're not going to measure parts per million this way. But maybe with CO2, you don't need to measure parts per million. Maybe you want to measure percents. I still think this is a technique that's not appreciated as much as it ought to be. So you might want to say, I want to know what ppm I can detect. Here's the fluorescent signal. Here's the fluorescent signal in the weak excitation limit. I'm seeing now that I'm getting a little bit behind in time, so I'm going to stop in a minute. You're going to use a pulse laser. We're going to integrate our signal. What we're going to do here. I want to do this in terms of pulse energy, laser line width. So I got to get back to this quantity over here, the integrated intensity. You can write this now in terms of the pulse energy. And when I do this, the fluorescent signal in this, I'm doing this in the weak excitation limit, and weak excitation limit first. I see that the fluorescent signal, written in terms of the pulse energy and the laser line width and the number density of absorbers and the path length and so on, doing the whole thing. When I do this, put in some numbers, now I'm saying, well, let's put in 10 microjoules. That's a pretty small number. 10 microjoules, that's going to put me in the weak limit. pulse length of 10 nanoseconds, laser line width, put in some numbers. When you get down at the bottom, you'll find that the fluorescence signal in photons can be written in terms of the, and for the numbers that I've used, can be written in terms of the mole fraction, which is 3 times 10 to the 7th. Hold it. 10 microjoules, and I can detect 10 to the minus 7? That's why the analytical chemists got excited about this. Now, we're not home free yet, because when you send in photons onto a photodetector, you don't get a conversion of 1 photon to 1 electron. You get a fraction. That's called the quantum efficiency of the photodetector. And so the quantum efficiency is the electrons produced per photon absorbed. That number might be 10%. I'm down now to something like this. For an ideal shot noise detection, where the signal-noise ratio of a photodetector is written as the square root of the number of photons. So I basically lose a factor of in this radical of 10. But it's still awfully good. The signal-noise ratio would be 3 times 10 to the 6 times the mole fraction. So even if I have a mole fraction of 1 ppm, my signal-noise ratio is square root of 3. Pretty impressive. Pretty impressive. Signal-noise ratio is 1.7 for a 1 ppm. Pretty impressive for a non-intrusive measurement made in a 1 millimeter volume, cubic millimeter volume, in 10 nanoseconds with only 10 microjoules of power. So that's why this is so exciting. However, the two-level model doesn't apply exactly. Now you might say, well, I could do even better. Let's go to the saturation limit. I'm going to send in more photons. I've got a joule. I don't need 10 microjoules. If you go through the same exercise, and you'll have to just read it yourself, you pick up a little bit. Signal-noise ratio becomes 5 for 1 ppm. So you pick up a little bit more, not as much as you might guess. So if you can saturate, the detection limit could be as low as 40 parts per billion. So at this point, it's looking pretty promising. The big thing is we haven't really recognized the influence of collisions to distort the two-level model. And it's harder, because when you populate a molecule, saturate between 1 and 2, the neighbor quantum states want to play in the game, and they'll either deplete or augment. So there's some perturbations to this theory that have been done in the literature over time. For the most part, people don't use saturation, but there are times when people do. Pulse laser excitation. I just want to now talk about characteristic times just briefly before I quit. A typical pulse length of a laser might be 5 to 20 nanoseconds. Might look something like this. I want to talk about characteristic times. What kind of let me see if I can jump down to this. Okay, the question should be, if these times are so short, is it still okay to assume steady state? That's really the question. If I go back to my steady state relationship, the question is this okay? Is it fair game to assume that the steady state time, the time to achieve steady state, is shorter compared to my laser excitation rate of 5 to 20? That's the question. And I'm going to go through this quickly. The fact is, if you go through these numbers, I like to define a characteristic time. The change that must occur in the signal divided by the rate of change. So if you extrapolate this linear line, that's one way of defining a characteristic time. So the question is, if you turn the laser on and if you're going to try to populate N2, it comes up this fast, how long is that? Then you turn the laser off. So you assume that the laser has this square shape. Then you turn the laser off, what happens? This is the figure that you want to understand. How long does it take to achieve steady state compared to my laser pulse width? And how long does it take for the signal to decay? And if you look at this, you'll see that and if you use my definition of characteristic times, you would find that the steady state time is 1 over the sum of all these terms. What's the dominant term? Well, it depends. It might be Q, or it might be W12. But it can be, oh good, I'm going to change batteries here in a minute. So, but the key point is the steady state time is 1 over the sum of these terms. The decay time, you take the w's away. So the decay time is long. It may still be a short number. If Q is 10 to the 10th, it's a fast time. But notice that because this steady state time is really short, it can be really short, and therefore the assumption of steady state for even a 10 nanosecond laser is good. Okay, that's there's 2 cases, weak excitation, strong excitation. I'm gonna let you study this. And I'm gonna skip the next slides and let you read them because they're pretty dense. And all of these slides are gonna tell you that there are regimes in which the 2-level model still works, even for molecules. And that's really a really important point that's not brought out in a lot of books. Okay, so what have we learned? LIF is spatially resolved from a point or a line. You can do this with a narrow sheet, and that's called PLIF. And it's especially useful for small diatomic radicals. I guess that's it. All right, that's what we're gonna, in the next hour, we'll talk some more about. We're gonna probably move into PLIF. That's really a motivation for LIF, kind of the limits of what you can do. And that simple 2-level model is not that hard. You can question whether or not it's when it applies, but if you're in the weak excitation limit, called the linear limit, the signal is proportional to N2. What is N2? The trouble is, it depends on Q, and nobody knows exactly what Q is. You got to measure it, and that's a trick. We'll talk about that. Okay, see you at 10.